So I thought it would be helpful if I did a little recap video which talks about finding tangent planes to surfaces, and then also about the gradient of functions in two variables, because there are quite a lot of links there, and then finally just chatting a little bit about the gradient of functions in three variables and how that is slightly different from the two variable case. So we're going to start off with a pretty straightforward example. We're going to say, suppose we want to find the tangent plane to the surface z is equal to x squared plus y squared at the point 1, 2. So the kind of surface that we're looking at is a paraboloid, like we could easily envision, and you can see we've got the point 2, 5, just 1, 2, 5 just sitting there. So I got that 5 from just substituting x equals 1, y equals 2 in, and then I know that the z coordinate is 5. And we want to find the tangent point, the tangent plane to this paraboloid. What do we need in order to find the tangent plane? Well, it's a plane, so we need what we need whenever we find a plane. We need to have a normal vector to the plane, and we need to have a point on the plane. Well, we've got a point on the plane because we know exactly what that is, and we also know it's 1, 2, 5. So the main thing that we're going to have to find out is a normal vector to the plane. And since the plane that we're interested in is tangent to our surface, when we're finding a normal vector to the plane, what we're really doing is finding a normal vector to the surface. So we want to find some vector that is orthogonal to the surface. So to think about how we're going to do that, we are going to first find two vectors that are tangent to our surface, because that's a little bit easier, we know how to do that. And then once we've got two vectors that are tangent to our surface, we can take their cross product, and that will be a normal. So just switching over to Geogebra so that you can get a feel for what we're going to do. Here's our paraboloid and there's our point. And what we're going to say is, well, if I look at the partial derivative with respect to x at that point, what I'm doing is I'm fixing y. So here I've got the plane y is equal to 2. So by fixing y, I'm really just looking in the x direction, and I'm seeing how z changes with respect to x. So I'm really just interested in what's happening on this parabola here. So what we're doing when we find our rate of change with respect to x holding y constant, so when we find our partial derivative with respect to x, is that we're looking at how fast our z value changes if we make a small change in x without changing y. So if I look at the drawing, I've just taken a screenshot, what we're finding is the slope of this line here. So this slope here is our partial derivative with respect to x evaluated at the point that we're interested in, which is 1, 2, and it happens to be 5. Okay, how does that help us with finding a tangent to the surface at that point? Well, we know that that line is tangent to the surface because that's what it means to be a derivative. So if we can find a vector in that direction, then in the direction of that line, then we're good. But what must that vector look like? So we want to find a vector along this tangent line. Well, what can we say about this vector? It's going to have I, j, and k components. Let's think about what they must be. Well, we know that that vector lies along the line where we're holding y constant, so y can't change at all. Our vector can't have a y component. So the j component here must be 0. Okay, so that was pretty straightforward. What do we know about the direction of our vector here? Well, we know that if we change 1 unit of x, it must change by an amount df by dx, because that is the slope of that line. So what we can put in here is we can say, well, this vector must change 1 unit in x, and as a result of that must change by df by dx evaluated at 1, 2 in the k direction. So this is just saying this is the vector that represents the rate of change in the x direction. It says if you make 1 unit change in the x, then you'll get a df by dx change in the z. All right, so let's put that all together. So I'm calling this one my tangent 1. And if I just simplify this a little bit, then I get that my tangent 1 vector looks like I hat plus, so I'm wanting my partial derivative evaluated at 1, 2, which we figured out over here. So that's just going to be 2k. All right, and then we can play exactly the same game, but in the y direction. So now we do the same thing, except we fix x. So you'll see here I've fixed x, and I'm just looking at what happens as I change y. So we can do the same calculation here. You can work out the partial derivative with respect to y, evaluate it at the point 1, 2, so that gives you 4. So that says that if I look at the line tangent to the point that I'm interested in here, this will have a slope of 4. And now to put this into vector format, so now we want again to find a vector that is along our line. Well, we think about what the components need to be. So let's think about the I hat, j hat, and k hat component. Well, we've fixed x, so our vector is not allowed to have a component in the x direction, so that's going to be 0. What's happening in the j direction? Well, the whole point of using our partial derivative here says that the slope of our vector says that if you move 1 unit in the y direction, you will move df by dy units in the k direction, in the z direction. So we have the same thing that we had when we did t1. We're going to have 1 unit in the j and df by dz units evaluated at the point that we're interested in the k. And we're going to call that t2. So putting this all together, we have that our t2 is equal to 1 in the j direction plus 4 in the k direction. Okay, so now what we've got is we've got 2 vectors that are tangent to our surface. So these 2 vectors lie on the plane that we're interested in. They lie on the tangent plane that we're trying to find. So t1 and t2 lie on the tangent plane. And we know that they're not parallel to each other because one has an x component but no y component, and the other one has a y component and no x component. So if we take the cross product, we're definitely going to get some vector that is perpendicular to both of them. And that is going to give us our normal. So we take as our normal, now I'm following the convention in the textbook here, which says take t2 cross t1, and it's just because you end up with a slightly nicer formula, but you could take t1 cross t2 and you'd still get a normal. You still end up with the same equation. It's just it's got some minus signs, which might be bugging. Okay, so following the textbook, we take t2 cross t1. So let's put that into our determinant. So I've got an I hat and a j hat and a k hat. And let's make sure that I get these right. So I and 2k, so that's 1, 0, 2. And it should not be 1, 0, 2 because that is my t1, and I want t2 to go first. So I should have 0, 1, 4, which is my t2, and then 1, 0, 2, which are the components of t1. And if I multiply this out, I will get 2i hat plus 4j hat minus k hat. Okay, so this tells me that my normal vector to the plane that I'm interested in is given by this bunny over here. So we're going to hop over to Geogebra and just check what this all looks like. Okay, so what have we got? Well, if we have a look over here, in blue, I've kind of highlighted the intersection between our surface and the plane y equals 2. And you can see the blue vector that is tangent to that line and therefore tangent to the surface, moving in the x direction, not in the y direction. So if you move around here, you can see our little vector, it only moves in the x and z directions and not in the y directions. So that's our t1. On the other hand, in green over here, what we've got is the intersection of our surface and the constant line x is equal to 1. And in green, I've got a vector, you can see pointing there, that's tangent to that curve and therefore to our surface. And again, if you have a look at this, you can see that our vector is only changing in the y and z directions, it's not changing in the x directions. So moving this around a little bit, you can see I've now got my two vectors here that are tangent to my curve. And so when we take the cross product of those, so we took t2 cross t1, what do we end up with? Here we go, this is the one that we calculated, our normal vector, and you can see that it is pointing straight out. So that looks absolutely correct, which is great. Okay, so hopefully now we're pretty much back to just finding the equation of a plane. All we need to do is take that normal vector, take the point on the plane that we know, and put it all together. So we've got our normal vector, and we take our point, which we know is 1, 2, 5, and we use the equation for a plane, which says that the normal dotted with any vector on that plane, which is given by a point on the plane and subtracting off another point on the plane, which will give you any vector on that plane, must be equal to 0. All right, let's plug in what we know. So we've got 2, 4, minus 1, and we're going to dot that with x minus 1, y minus 2, z minus 5, and that all needs to be equal to 0. If you do the maths, then do some little simplifying steps, and you should find out that the equation for this tangent plane is 2x plus 4y minus z is equal to 5. Okay, well, let's head back to Geogebra and just plot it and see that it makes sense. Okay, so here's what we found so far, and what happens if we plot the plane that we think we've worked out. Here it is. So there we have our tangent plane, we've got our normal vector, and you can see that the green and the blue vectors which we found lie on the tangent plane. Okay, so we've finished the first part of our quest, which was to revise findings tangent planes to surfaces. What happens next? Well, next we're going to look at the gradient and see that there are actually a lot of overlaps between the two. And in fact, you can use the gradient to find the tangent, to find the normal, and vice versa. So heading back to the notes. Okay, so just to remind you, we're going to start by defining our gradient for a function of two variables, so something like the one we've just been working with. And it is just simply defined as, and I find it more helpful to see it in this form, the gradient is the partial derivative of the function with respect to x in the I direction plus partial derivative with respect to y in the j direction. So looking at this, what we can see straight off is that our gradient is a vector. For example, if we are taking the example we've been working with so far, what is our gradient of our function? It is going to be partial derivative with respect to x, so that's 2x in the I direction plus 2y in the j direction. And if we want to talk about what our gradient is at a specific point, then we just plug in the points as you might expect. So we plug in the point 1, 2, and we're going to get that our gradient is 2 in the I direction plus 4 in the j direction. So our gradient is a vector, and more than that, although we have a surface that is in 3 dimensions, so we have x, y, and z coordinates for any point, our gradient is only defined as having x and y coordinates. So it lies parallel to the xy plane. Remember, vectors don't have a specific starting point. We can think about them starting wherever we want them to, but they do have a direction, and ours lies pointing somewhere in the xy plane. It never has a z component. Okay, so in terms of our function, what does this vector look like? Let's plot that. Well, here I've plotted our vector in two possible places. So I've just plotted our 2, 4 gradient vector starting at the origin, which you can see. But I've also shifted it, because vectors can start anywhere, to starting at the point that we're interested in, 1, 2, 5. So what does it look like? Well, it's a vector pointing out from our surface, something like this. And you might be thinking, well, okay, give me more information. So one thing that we can do is we can plot the level surface. So I've just set z equal to 5 and plotted the intersection of that plane with my surface. And if you do some kind of swiveling around, the thing that you'll notice is that our gradient certainly looks like it's normal to the level curve. So it might be tempting to think, well, hang on, isn't our gradient just the same as our normal? No, it's not. So let's just go and plot our normal. No, that's not our normal. Where's our normal? Nope. Here's our normal. There's our normal. So our normal has a z component. But as we've said, our gradient doesn't have a z component. But there's a lot going on that is similar. So if we now look again from the top, you'll see that in terms of x and y components, our normal and our gradient are definitely pointing in the same direction. The only difference is that our gradient doesn't have a z component, whereas our normal does. So let's just go back and look at the equations, and you will see the link straight away. Okay, so pulling together our normal vector and our gradient, let's have a look. So I've just taken a kind of snapshot from the side so that you can see that our gradient and our normal point in the same xy direction. Well, you can't quite see that from here. I should have done a top-down view as well. But the other thing that you can see is that our gradient lies in the xy plane. So it's pointing in the xy plane, but our normal vector has a z component. And if we have a look at the equations that we found for both of these, you'll find our normal is 2i plus 4j minus k, and our del f, our gradient, is 2i plus 4j minus 0k. And you might be suspicious, and you will notice that our components in the I direction are the same, and our components in the j direction are the same. Is it a coincidence? Well, no, it's really not. If you go back and check where this 2 came from, this 2 came from evaluating df by dx at the point we were interested in, which is 1, 2. And similarly, straight from the definition of the gradient, so does this one. So actually it would have been weird if they weren't the same. And similarly, this 4 over here, we found from the partial derivative with respect to y, evaluated at the point we're interested in. And again, straight from the definition, the gradient requires that this coefficient here also be the partial. Okay, so it should be no surprise that in terms of x and y direction, these two vectors are exactly the same. The only thing that changes is that our gradient has a 0 component. Let me put that in a different color. Our gradient has a 0 component in the z direction, whereas our normal has a -1 in the k direction. Now, the one thing that I just want to highlight is this -1 that we got for our normal over here. You would get a -1 no matter what function you were dealing with, because that -1 came out of the cross product that we did up here. If you have a look at this determinant, which I've now mangled horribly, let's try and clean this up a little bit. If you look at where all these numbers came from, the 4 and the 2 came from our partial derivatives, but these 1s just came from the fact of how we constructed our normal vectors, our tangent vectors, which was just based on the fact that we were having a change of 1 unit in the x direction, which resulted in a df by dx change in the z direction. And similarly, we had a 1 change in the y direction, resulting in a df by dz. Oops, that shouldn't be a z, that should be a y over there. A 4 unit, which was df by dy evaluated in the k direction. So going back to what we've got over here, in this determinant, any time that you've constructed tangent vectors the way we did, you'll have a 1 in each of those spots and 0 in each of those spots. And it will only be your k components over here which will depend on the particular partial derivative that you found. So if you have a look at the final solution that you get over here, the 2 and the 4 will depend on the particular function that you're dealing with, but this minus 1 over here is always going to be there. You can check it for yourself, but the net result is that for any surface that is well behaved where you can find your partials the way you might want to, your normal vector is going to be your partial with respect to x evaluated at the point that you're interested in, giving you your x component. Your y component is given by the partial with respect to y evaluated at the point you're interested in, and then your k component is just minus 1. So you can check for yourself and make sure that you're happy with that derivation. So, to finish off, you can move between the normal vector to the surface and the gradient very easily once you know your partial derivatives. So if, for example, you're given your gradient, so you know that it's 2i plus 4j, you can immediately say, well, the normal is going to be 2i plus 4j minus k. On the other hand, if you get given your normal vector, so you know that it's 2i plus 4j minus k, then you just get rid of the k term, and that's going to be your gradient. So the two are integrally linked, but they're not usually the same. So challenge for yourself, think about when will the gradient and the normal be the same? When could that happen? Okay, so we've talked about surfaces. So these are functions of two variables. So we've got z is equal to some function of two things. And we've said that you can find normal vectors, which we've done, and you can find the gradient vector, and the gradient vector is always going to be parallel to the xy plane, and it's going to be normal or orthogonal to the level curve. Good so far. What happens if we go up a dimension? So there's no reason why we can't define the gradient in exactly the same way, but now we're thinking about functions of, for example, 3 variables. So what I've done here, just created essentially the 4-dimensional analog of the 3-dimensional paraboloid that we were looking at. So I've got some variables, so I'm just to make sure that we're clear, we've got something new here. I'm going to say w is equal to x squared plus y squared plus z squared. So I think one of the examples I might have given in class, here you might be thinking of the temperature depending on the location within a room. So if you want to map the location in a room, you need 3 variables, an x, y, and a z, and for each point that you have, you will then get a resulting temperature. So that's the kind of thing that we're looking at over here. And we are defining our gradient in exactly the same way. So partial derivative with respect to x in the I direction, with respect to y in the j direction, and now we just add on another dimension because we've gone up a dimension. So partial with respect to z, which is now an independent variable in the k. Okay, straightforward. What can we say about this? Well, the first thing that I want to think about is what does this function look like? And it's always going to be a little bit tricky, but remember we have tools that we can use to visualize functions in higher dimensions. So just to kind of get you thinking what it is that we're really looking at, if we were in 2 dimensions, we would be looking at a function like f of x is equal to x squared, which you know and love. It looks something like this. Okay, when we went into 3 dimensions, which we've just been doing, we had something like f of xy is equal to x squared plus y squared. So now then you would get your paraboloid, which does something like this. So you have an extra dimension coming out here. So when we go up a further dimension, we're looking at something similar, but we can't kind of visualize it. What can we do about that? Well, use the idea of level curves. So if you wanted to, although you probably never did when you were doing functions of one variable, you could fix a y value and just look at what was happening in the x, and you'd find that you would get 2 points. It is slightly more useful when we're thinking about a 3D function. So now we would set the z value and just keep everything constant there, and what you'd find if you kept the z value constant would be you'd have the circle of a level curve. So it's slightly more helpful here if you think about what happens in our 4-dimensional case. So we've got our f of x, y, and z is equal to x squared plus y squared plus z squared. In 4D, if we fix our w or our f of x, y, z, what we're looking at is some constant is equal to x squared plus y squared plus z squared. And depending on the value that we fix at, depending on the k, we'll get a different level surface. So this is our level surface. And we know it's a surface because it's got x, y's, and z's. What particular kind of surface is it? I hope that by now this is starting to be kind of ringing a bell. This is a sphere. So now we're thinking about our level surfaces rather than the level curves that we were thinking about when we were in 3D. But we're in 3D when we think about the spheres because they're surfaces. Okay, so when we were in 3D and we had a surface, we found the level curve, which looked like this. When we're in 4D, now we find the level surface. So we're visualizing in 3D, but what we're looking at is the level surface. We're not looking at the thing itself, okay, the function itself, because we can't. Okay, where am I going with all of this? You probably think I'm laboring it a lot, but there's a point to this. Well, if we calculate our gradient for our new shiny 4-dimensional thing, you'll find that it looks like this. So it looks quite a lot like the gradient we've seen already. 2x, 2y, and then it just has this 2z component. And we can calculate it at a specific point. So I've just chosen to add this component. So we're looking at the point 1, 2, 3, and we want to evaluate it. You'll find it looks like this. So what does this thing look like? So the key thing here, which is where things get a little tricksy, is if you plot the level surface at this point, you're going to get a sphere. Okay, so let's do that. Okay, so here we've got our level surface of our 4-dimensional function plotted, and the particular level surface is the one that goes through the point that we're interested in. So that's the point x equals 1, y equals 2, z equals 3. So you plug in x equals 1, so and so on, into our function x squared plus y squared plus z squared, and you'll get 14. And then if you put that 14 as your function value, so setting the level surface, you get 14 is equal to x squared plus y squared plus z squared, which is this delightful sphere that we've got over here. So this is the level surface. And if you go ahead and plot the gradient that we found, then it looks like this black arrow over here. And moving this around, you will see that our gradient is normal to the level surface. And this might be the moment where you think, hang on, I thought we said that the gradient wasn't normal to the surface, and we did. When you're in a function of 2 variables, your gradient is not normal to the surface, to your actual function, but it is perpendicular to the level curve. What happens in 3 dimensions, if you add a function of 3 variables, Now your gradient is normal to the level surface, so it is normal to a surface, it's just not normal to the actual thing that you're thinking of, which is in one higher dimension than you had before. So there's nothing hinky going on here, it's just the fact that we've gone up a dimension. We were dealing with level curves, which our gradient was normal to, and now we're dealing with level surfaces, and our gradient is normal to those. So yeah, nothing weird there, it's just this kind of going up dimension by dimension. Okay, so what can we say as the moral of the story? If you've got a function of two variables, then our gradient at a point is orthogonal to the level curve, and in fact the xy direction will point in the same direction as the normal, but it's probably not going to be the normal. It's not going to be orthogonal to the tangent plane at that point. On the other hand, if you've got functions of three variables, then our gradient at a point is orthogonal to the level surface at a point, and because we're now dealing with a level surface, that surface will have a tangent plane, so our gradient is going to be orthogonal to that tangent plane, but it's probably not going to be orthogonal to the tangent hyperplane at that point. So remember, you won't have a tangent plane to this crazy four-dimensional surface, you'll have a hyperplane. And we need a little bit more maths if we were to talk about what it means to be orthogonal, but our gradient wouldn't be. Okay, so hopefully that helped a little bit. I will also maybe upload a little video on finding extrema, but for the moment focus on making sure that you're really happy with working with tangent planes and gradients and all of that stuff.